right. So when I say between class variance, I say it is the variance of the class means. Okay. So I will take the classes, okay, I look at the means of those classes and look at the projected means of those classes and compute the variance among the projected means. Okay, suppose I have k classes, I can compute the variance among those. If I have 2 classes, what will this amount to? Maximizing the distance between the projected, right. If it is 2 classes, it will be maximizing the distance between them. If it is k classes, it will be maximizing the variance among the k centers, right. Relative to the within class variance, and what would be the within class variance? For each class, the variance with respect to the class mean, right. So that is what we already computed, that, right, but for each class, right. So within class variance, that is essentially what I am looking at here, right. So let us just treat the first condition alone. Right. So I will just simplicity sake start off with a 2 class case and then we can think of the generalization to multiple classes. So I am going to have a surface defined by W transpose X, right. So Y equal W transpose X, if it is greater than some W naught, I am going to classify it as class 1, if it is less than some W naught or less than or equal to, I will classify it as class 2, okay. Sorry, my font went too small. So I am going to say M1 bar and M2 bar are the means of C1 and C2, right, and well, we know how to compute M1 bar just like you do mu hat there, and I am going to assume that when I write the mk without the bar, okay, it is the projected one, okay. So W transpose mk hat essentially the projection of the mean, okay, in the direction W transpose, okay. So that is essentially what this is. So the reason I am using this funny notation is in the textbook, if this is bold it is M1, okay, if it is unbolded it is a projection, but I can't write bold every time on the board, so I am just using the bar, right. Then when you read the book you can translate back, and for this you read this part alone. So till that part it is from Hastey-Tibshirani-Friedman ESL, okay. This part alone you do PRML, pattern recognition and machine learning by Chris Bishop. The textbook reference is there on the right. So what is my goal when I say I want to maximize between class variance? It is essentially to maximize that quantity, right. So W transpose M2 is the projection of M2 on W, W transpose M1 is a projection of M1 on W. I am trying to maximize this quantity, so that is essentially my first criterion, right. Find the direction W that maximizes this, right. So there should be some alarm bells ringing for you. What is the problem? If I do not have any bounds on W, I can just arbitrarily scale my W and get larger and larger values, right. So I will have to have some constraints, right. Assuming summation over, so essentially norm W is 1, okay. That is an assumption we will make frequently to make sure that we do not get unbounded solutions, right. So this is numerically unbounded, okay. So where?
Yeah. Says that summation W is variable to 1.
Good question. So you could impose a inequality constraint saying that summation WI square is less than 1, but what do you think will happen?
Means it would be less constrained.
You are maximizing the value, right?
You just scale it until it is 1.
I'm sorry?
I mean, you can just increase the.
So you can just scale it. So essentially what will happen is you will scale it such that WI hits 1 anyway. So even if you are having even if you have the lesser than or equal to constraint, because you are maximizing over W, you will hit it, you will essentially scale W till you hit 1. So you might as well leave it as equal to 1, right. So you can solve this, right, but the take home message is that your W is going to be right. So W will be proportional, okay, you add that here, right, you take the derivative, W will go, that will become W. So there will be some constants here, right, but essentially you are going to get W will be in the direction of M2 minus M1, right. So what does this mean? Take the means, right, and if again you can go back and show that if it is spherical, then the constant will be half, right. So it will be the midpoint of the line dividing the two means, okay, right. So let's do it again. So I have two classes, right, I take the means, right. So this will be the direction of the projection, right. So I will have to project everything onto this, right, this way. So this will become class 1, that will become class 2, okay. Does it make sense, right? Yeah. So I mean this line and this line are actually parallel to each other. I know you really didn't want me to repeat the drawing, but I think that will help, okay. So I have class 1, I have class 2, right. So I mean if you look at the data point that comes to me, so do people understand when I say class 1, class 2 like this, do you understand what I mean? So this is the Gaussian corresponding to class 1, I am drawing the 1 sigma contour of that, right. This is likewise the 1 sigma contour of the second Gaussian. So the data point that comes to me could be something like this, right. This could be the training data that I am getting, right. So it will be mixed up of pluses and minus in this region, right. That could be minuses here also, okay, I already drew one, that could be minuses here, that could be pluses here, because the Gaussian still does extend beyond the contour I have drawn, okay. The contour is only the most probable region for the data points to lie, does not mean that outside this contour the probability is 0, okay. So this is essentially what it means. So I am going to get data like this, and I am going to model the, I am modeling the Gaussian by these contours, okay. Now let us say that roughly that these points are the centroids of the data that I get, right. Roughly these are the centroids of the data I get. So what this tells us is that, okay, you join these by a straight line, okay, and essentially you take a direction that is right like this and project all the data points to that, right. So you will get all the data points lying here. Now fix a threshold, that's what I wrote here as W naught. Pick a threshold such that above that it is class 1, below that it is class 2, right. In this case, in fact, if this had been spherical, you can show that the threshold would lie midpoint. Now we can't because well, you can, I guess, I mean depending on under special circumstances, but now the point will be somewhere here and all the data points which projected above this I will say it is plus, all the data points that projected below this I will say it is minus. Does that make sense? Okay. Right, but then this is not what we are looking for, right? Right, we are missing something important. What is that? The interclass, I'm sorry, the within class variance, right. So this is the interclass variance, the within class variance is what we are missing. So what we will do now is start looking at that, right. Right. So that is the projected mean, these are the projected data points belonging to class 1, okay. Keeping in with the terminology we are using there. So I am picking out all the data points, training data points which had class k, right. I am looking at the projected distance from the projected mean. This gives me the total within class variance, right. Yeah.
Aren't we supposed to divide by n?
Yeah, we are going to maximize everything at the end, so I am just ignoring the things that do not affect the maximization at the end. Okay. Yeah.
Could you explain how you got that square term?
Which square term?
The first line.
This one. So that is essentially this is the projected data and that is the projected mean. I am just taking the variance of that, right. This is exactly what we did there, except that I have not divided by the number of data points. Okay. Right. So this criterion is called the Fisher criterion. It's called the Fisher criterion after Fisher was a very famous statistician who came up with LDA. Okay. Several decades ago. So here I am going to do something confusing. Right, so I am going to rewrite it. Right, so this is the between class covariance matrix, right. So if you think about it, so what I wanted was M2 minus M1. What is M2? So the projected, right. So the projected one, so M2 will actually be W M2 bar, right, W transpose M2 bar, right. So essentially I have W transpose M2 bar minus W transpose M1 bar. So I can take out the W transpose and then have the square of the M2 bar minus M1 bar, and I am adding the W squared back in, okay, by doing W transpose SBW, okay. Now what about SW? Right. So likewise, so I have this as my Sk squared, right. So S1 squared plus S2 squared is essentially, this is S1, right, and I take out the W from there, and this is S2, I take out the W from there. So that gives me the W transpose SW W, right. So now what we want to do, we want to maximize this, right, we want to maximize the between class variance relative to the within class variance, that is what we said, right. Between class variance is maximized relative to the within class variance. So that is between class variance is within class variance, I have to take the ratio, now I am maximizing this ratio. So differentiate with respect to W. Differentiate with respect to W and set it equal to 0, right. So this is what U by V, right. So people want to tell me what the differential will be? Okay, I will write it, but you should recall all of these childhood memories, okay. You should not forget whatever you studied to get in here. Right, so the denominator in the thing will become 0 because I have equated to 0 already. So when you take the derivative of this, you are going to get some term in the denominator, right. So that will go to 0. So I will just have to equate the 2 halves in the numerator and I will get this, right. So just refresh your derivatives. The only thing that I am pretty sure putting everybody off is the fact that we are doing all of this in the matrix notation, right. Just practice it, makes life a lot easier, do it a couple of times, right. Okay, the best way to do it is try and write it out in matrix form in gory detail, okay, do the term by term derivative of it and then look at how it simplifies after you do the derivative, right. Then you will see the pattern and then you will know exactly what we are writing here, right. So very simple things, like there are quadratics, so you should know how to differentiate quadratics, that is the only thing that is throwing you off, right. W transpose W is actually a quadratic in W, right. So that is the only thing, so it becomes a linear in W, right. So that is all, nothing more to it, right. Actually if you think about it, SBW, okay, will always be in the direction of M2 bar minus M1 bar, right. So you already saw that here when we had only the constraint on SB, right. So here the constraint was only on SB, right, only on the between class variance. When we had the constraint only on the between class variance, we ended up finding out that the solution is going to be in the direction of M2 minus M1, okay, and a little bit of work you can show that always that SPW will be in the direction of M2 minus M1, right. So I can actually drop that and replace that with a vector proportional to m2 minus m1, right. So now it makes our life a lot easier, right. I only have one w left. So what about these guys? They are all simplified to some kind of scalar quantities, right. So finally what I will get is w is not equal to but proportional to so that is essentially what I will get. So if I did not have the SW constraint, what I got was w was proportional to m2 minus m1, right. But now if I am taking into account the within class variance also, then I will have to pay attention to the within class covariance matrix. So that is what this was, right. I will have to pay attention to the within class covariance. So that is basically all that is to it, okay. But how does this relate to this? I see any relation between this and that? Think about it, that is basically what we are doing there, right. So sigma inverse is SW inverse, right, just using different notation here, right. So SW inverse is just taking the variance between the in the data, right, in the within class variance. So sigma, if you remember, is the within class variance matrix, right. So that gives me sigma inverse here, and this I got the sigma inverse here, and then I have m2 minus m1 and I have mu k minus mu l here. So essentially for I mean modulo all of these other non x related terms, right. So we are essentially finding the same direction, right. So whether you do it this way, starting with that as your objective function, right, between class variance and within class variance, or you start off by saying that your class condition density is Gaussian and then you are trying to find out the separating hyperplane, right. So in both cases you end up with the same direction modulo some scaling factors, right. So you can use either motivation for deriving it, but what is the nice thing about this motivation? We did not make any assumption about the class condition distribution. The Gaussian assumption is missing here, right. The Gaussian assumption is missing and we worked only with sample means and sample variance and so on and so forth, right. So it just tells you that LDA does not work, right, only when the distributions are Gaussian, right, they are fine. Even when the underlying distribution is not Gaussian, there is actually a well defined semantics to doing LDA, right. People are with me on that so far? Okay, great. So any questions? Now let's have to move on to the next thing. G of W?
What does it represent?
This one, G of W, I told you, right. So I want to look at the between class variance relative to the within class variance, right. So the numerator is the between class variance and the denominator is the within class variance. So I am trying to maximize the relative score.